SwayamPrabha. Digital India. Educated India.
सहनावतु सहनौ भुनक्तु सह वीर्यं करवावहै तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
This will be lecture number 16, mechanical measurements. Towards the end of the last lecture, we were looking at the measurement of transient temperature, and we discussed 3 different cases. And the last case, that of sinusoidally varying temperature, was not completely covered in its entirety. And therefore, what I am going to do in the present lecture is to start with that particular case and look at the details of how the response of the system behaves with the sinusoidal input, and then we will give an example which I call example 16. I will work it out on the board, and then I will look at resistance thermometry. 2 different aspects are there. One is the platinum resistance thermometer, which is very often used, and many times we also use what are called thermistors, which are also the temperature sensors, where the resistance of the element changes with respect to temperature in definite fashion. So, to begin our discussion, let us look at the response of a first order system, a temperature sensor treated as a first order system. I am subjecting it to a periodic input in the form of the function Ta cos omega t, where omega is the circular frequency and Ta is the amplitude. And initially the temperature of the system and the sensor are not the same, they may be different, and then starting from t equal to 0, for t greater than 0 we are going to input the sinusoidal variation of temperature of the ambient fluid. If you remember, the general solution was obtained, and then by putting the appropriate form of t infinity as a function of time on the inside the integral, after integrating it twice, we get back the integral, and therefore we will be able to find out the response in terms of the amplitude reduction factor and the phase lag. The output is again a sinusoidal, that means there is no change in the shape of the variation with respect to time, only the size is changed, that is the amplitude is changed, and also there is a phase lag, that means that the response of the system lags behind the response or the input which we are going to provide. The important parameter which is going to play a role in this particular case is the product of omega, the circular frequency, and the time constant tau, omega tau product. Of course, omega tau product can go from anywhere from 0 to infinity in principle, that means very small values to very large values. If omega tau tends to 0, obviously it is like steady state, there is no variation with respect to time, and when omega tau tends to infinity, that means that the input frequency is very high or the time constant is very large, one or the other. And in fact, the figure I have drawn here shows the logarithm of the omega tau product on the x axis, and on the y axis I have either the amplitude reduction factor, which was given by 1 over square root of 1 plus omega squared tau squared, or the phase lag, which was given by tan inverse of omega tau, and I have divided the phase lag by 90 degrees, so that I can normalize the phase information and put it both the amplitude reduction factor and the phase lag become normalized, and therefore, they lie between 0 and 1. What we notice is that when omega tau tends to 0, the phase lag tends to 0 and the amplitude factor tends to 1, and when the omega tau product becomes very large, in this case I have taken up to 100, you see that the amplitude reduction factor is almost 0. That means that there is no response. The periodic input is not indicated. That means there is no response of the system to the input, which is very high frequency. The tau, the time constant is very large, and therefore, it is not able to respond to that. So, it will just show an average value, and you will also see that the phase lag approaches 90 degrees as omega tau product becomes infinity or very large. There is a crossover, and you can see that, in fact, if I plotted logarithm of on this axis, it will show a nice behavior. It will be almost like straight, and then it will drop down straight according to straight line kind of relationship at this point onwards. So, the typical case I take, for which I can plot the response in the real time temperature time graph, so that I can appreciate what is going on. So, if I have the temperature ratio T divided by T naught plotted as a time function of time, and the input is T A by T naught equal to 0.25, this is the amplitude is 0.25 times the initial value, and the omega is 1 radian per second. I have just taken a particular case, and tau equal to 1 second. So, that omega tau product is equal to 1 in this particular case, and you will see that the input response or the input, the variation of the temperature is according to this relationship. It starts with a value of 0.25 at t equal to 0, and it cycles according to the formula T A by T naught is equal to 0.25 cos omega t, and the output, it starts initially from value of 1, because T by T naught equal to 1 at t equal to 0, and then initially there is a transient wherein the output response falls quite drastically, and then immediately it starts responding to the variation which is periodic, and therefore, quickly the solution or the output response tends to become a sinusoidal, as shown by this curve, and we notice that the amplitude of this curve is smaller than the amplitude of the input, and that is one of the consequences of the periodic input in the case of a system of first order system with a given tau. You will also notice that the input is reaching a maximum, and sometime later the output response of the system is catching up with it, and it is giving a value which is of course lower, but the maximum is shifting with respect to time. Therefore, time lag is there. In fact, I can measure the time lag by taking the phase lag. Phase lag is nothing but we can interpret it as omega times some t lag, and therefore, omega t lag is equal to the phase lag, and therefore, phase lag divided by omega will give you a time lag equivalent to time lag. So, in this case you see that there is a time lag of something like between 1 second or whatever equivalent of that, okay, because omega is equal to 1, tau equal to 1, there is a time lag like this. So, the response for a particular case is shown here, and let us now look at what is going to happen in a general case. So, if I look at the general case, I am just going to make a very simple analysis without too much of mathematical details, so that we understand what we are talking about. So, if you remember what we did, we had a periodic input at one single frequency omega. We can call this as the fundamental frequency. That means that I have a wave varying like this, and this is the period of the wave, this is the amplitude, and this is a sin or cos omega t. The difference between sine and cos is that they are shifted with respect to each other by 90 degrees. That is about. Okay. Suppose instead of this, let us say I have a slightly the same wave with a something like this. This is again T. This has many more small wiggles here. That means this is a composite wave. That means that it is going to be given as a sum of terms like this. Okay. We can in fact write what is called a Fourier decomposition. And I will just briefly indicate this Fourier decomposition in the next page. So, what we are going to do is the wave is split up into omega, 2 omega, 3 omega and so on and so forth. That means that the original wave is now consisting of a fraction of this, a certain fraction of this, etc. That means that I am going to have, we can say that I can write it as A1 cos omega t plus A2 cos 2 omega t plus etc. Okay. So, in other words, the original wave is now made up of components where A1, A2 etc. are to be determined by comparing the series with the original wave, and using the Fourier series method we can do that. Let us not worry about it right now, because it is not of importance to us. We want to just look at the how the solution is going to be there. The first component is at omega, the second one is at 2 omega, and if you remember, the amplitude reduction factor for this will be 1 plus omega squared tau squared under square root of, and this will be 1 over square root of 1 plus 2 omega tau whole square. That means that this is greater than this, and this will be greater than the third term, it will be 1 over 1 plus 3 omega tau whole square and so on. That means that the different components of the waves which are present in the original wave are going to be attenuated with respect to attenuated or the amplitude reduced by different amounts. This is smaller, this is less attenuated, this one is more attenuated and so on, and therefore, we will get a change in the shape of the wave, that is number 1. And number 2, also this will be phase lag will be tan inverse omega tau, this will be tan inverse 2 omega tau and so on and so forth. That the phase lag is also changing. That means, there is a shift in the wave or the shift in the response with respect to time, and also there is a change in the direction, a change in the amplitude of each one of these components. Therefore, you are going to have some distortion in the shape of the wave. The output will be now a complex wave which is going to consist of several components, each component attenuated to different extent and each component having a different amount of phase lag with respect to the original wave which we have given. So, the idea with which we have done this exercise is to just look at what happens to one component, and then if we understand that, we will be able to understand what happens to the other components, and therefore, when we have a original wave which is a complicated shaped curve, not a pure sinusoidal, you can always look at the overall response by looking at the component responses and then adding them and getting the response to the system, because the system is essentially a linear system. So, we will say that this is a linear system and the response is made up of all these components. In most applications, we may be interested only in the fundamental more or less, and therefore, many times we need to worry only about the first term in this series, but there may be occasions when you want to look at the other terms also, and it can be done by this particular method I have indicated. So, with this background, let us look at a simple application of what we have done. This is the example number 16. which I am going to just indicate by looking at a simple case. I have a small foil type sensor. This is aluminum foil with a small thickness, and it is subjected to a heat transfer coefficient of 50 watts per meter squared degree Celsius, and the size of the foil, it is given by 0.025 meters multiplied by 0.03 meter multiplied by the thickness is 0.405 meter. Okay, this is the size of the foil, and the foil is losing heat by with a heat transfer coefficient H equal to 50 watts per meter squared Celsius. And the properties of aluminum, the value of C, the specific heat capacity is 903 joules per kg Kelvin or kg degree Celsius, and the density of aluminum is 2700 kg per cubic meter. If you remember what we have discussed earlier, the volume to surface ratio, assuming that it is losing heat from both the sides, that is this side as well as this side, it is nothing but delta by 2, where delta is the thickness of the foil. Okay, half the foil thickness is the volume to surface area ratio. What I would like to calculate, there are three things which I am going to do. One is I will calculate first the time constant tau, which is easily calculated by using the formula tau is equal to the mass specific heat product divided by the area heat transfer coefficient product, and this is written as rho C V divided by H S, and V by S we have just now seen is rho delta by 2. Therefore, this becomes rho C by H into delta by 2. Now, I can plug in all the values. Rho is 2700, C is 903, H is 50, and delta is 0.00005 divided by 2. So, the time constant comes to 1.219 seconds. So, the time constant of this particular system is 1.219 seconds. Now, let us look at a typical case where a periodic input is at 0.1 hertz frequency. We would like to find out what is the amplitude reduction, and also we would like to find out what is the time lag, what is the phase lag. So, it is very simple to do. So, if you remember, if is the, this is nothing but f the frequency, omega will be given by 2 pi times f, that will be 2 into 3.14159 multiplied by 0.1. This will be radians per second, and this works out to 0.628 radian per second. So, we can find out the omega tau product, and the amplitude factor is nothing but 1 over square root of 1 plus omega tau whole square, 0.628 multiplied by 1.219 is whole squared, whole under the square root sign. This comes to 0.794. So, only 79% of the input amplitude is registered by the sensor. We can also look at the phase lag phi equal to tan inverse omega tau, which is equal to tan inverse omega is 0.628 multiplied by 1.219. This will turn out to be 0.654 radians, and in terms of angles this will turn out to be about 37.5 degrees. And as I indicated earlier, the time lag is nothing but phase lag divided by omega. So, that will be 0.654, and you should remember that we have to use the phase lag in radians, not in degrees, for the calculation of the lag in time. This will be divided by 0.628 . This will give you about 1.04 second. That means that the maximum indicated by the sensor will be after 1 second, almost 1 second, a little more than 1 second after the maximum actually occurs in the temperature which is varying. There is a 1 second lag between the two. And the third case I am going to consider is if there is a ramp input, that means that the temperature T infinity is varying linearly with respect to time at 0.5 degrees Celsius per second. What is the lag in the temperature? So, we will say that is the temperature lag as T tends to infinity. In this case, T must be greater than about 5 tau, let us say, and tau is almost 1.2 second. This will be equal to 5 into 1.2 roughly, and this is about 6 seconds. For time greater than 6 seconds, you can expect the temperature to lag by an amount equal to R tau. R is 0.5 multiplied by 1.219. This is so many degrees Celsius, and this comes to 0.61 degree Celsius. That means there is a 0.6 degree difference between the temperature indicated by the sensor and the actual temperature of the ambient, which is varying with respect to time according to a ramp input. So, this sort of completes our discussion on the transient temperature measurement, and then we are ready to go back to our main theme of measuring temperature. In this case, I am going to look at the resistance thermometry. Two thermometers I am going to look at: the resistance thermometry or resistance thermometer, platinum resistance thermometer in particular, and then I will also look at the case of thermistors, and we will see where these two things, these two types of sensors are useful, and we will also look at in detail how to use them and what are the characteristics of each, and so on and so forth. So, the basic idea of resistance thermometry goes back to what we said several lectures ago. The idea is to see if there is a definite relationship between the temperature and the property of the resistance thermometer, which is the resistance, electrical resistance. If there is a definite one-to-one relationship between temperature and the resistance can be used as a thermometric property, and the resistance thermometer can be used as an instrument to measure the temperature. So, the resistance thermometry depends on the unique relation that exists between resistance of an element and the temperature. And let us look at some of the resistance elements which are used in practice. I have indicated 3 of them: nickel, then copper and platinum. Of course, platinum is the most common, others are not that common, but they are also useful and used. So, we have 3 different materials: nickel, the temperature range in which it can be used is -60 to 180 in degrees Celsius, and the characteristic is given by specifying the resistance of the element at 0 degrees Celsius and 100 degrees Celsius. There is only one C here. So, the nickel can be used between minus 60 and 180. The value is 100 at 0 degrees Celsius, then the value at 100 degrees Celsius is 152. Therefore, almost 50% change in the resistance between 0 and 100 degrees. Copper is useful between minus 30 and 220. It is 100 and 139. Of course, this is less sensitive than this one, because this variation of nickel is more than in the case of copper. And in the case of platinum, it is useful from minus 200 to plus 850 degrees Celsius, and the variation of the resistance is 100 to 136, about 36% variation between 0 degrees and 100 degrees. So, this is the ice point, and this is the steam point. So, I am talking about the ice point and the steam point, and the variation of the resistance is something like 100 to 136. The main difference between resistance thermometers and thermistors, which we will see later, is that this variation of resistance is very small in the case of resistance thermometers, and the resistance increases with temperature. In the case of thermistors, it is going to decrease with respect to temperature and also decrease by a larger fraction, and therefore, thermistors are more sensitive, but they have a smaller range compared to the resistance thermometers. The case being, we are talking mostly about the platinum resistance thermometer. So, the platinum resistance thermometer is also referred to as PRT. PRT is nothing but P is for platinum, R for resistance, T for temperature, or it is also referred to as RTD. RTD is simply a resistance temperature detector. So, RTD can refer to any resistance temperature detector, but PRT will refer to only a platinum resistance thermometer. So, these terminologies are used very extensively in the literature, in books and so on. So, you should not be confused. If you see PRT, you know what it is, or RTD. RTD is a very general term used for resistance temperature detector. We shall take the example of PT100. In fact, if you remember, if you look at the previous case, I took the element resistance at 0 degrees Celsius 100 ohms. So, this platinum having a resistance of equal to 100 ohms at 0 degrees Celsius is called the PT100. PT100 means platinum resistance thermometer with a resistance equal to 100 ohms at 0 degrees Celsius, that is the ice point. This is the standard element which is used in practice, PT100. Of course, you can also have PT with a different value of resistance. That means that the number of turns or the length of the wire and the cross section of the wire have to be taken suitably, so that you can get different values for the resistance. And we also know that, as we explained in the earlier case, resistance increases with temperature, and this is shown graphically in the next graph. So, we have the terminology I have used here is the relative resistance. Relative resistance is nothing but the resistance at temperature T divided by resistance at the 0 degrees Celsius. So, this is called the relative resistance, and you can see that the relative resistance is equal to 1 at 0 degrees, because that is the reference anyway, and for temperatures below the room temperature or below the ice point, the ratio is smaller than 1. That means the resistance is decreasing with respect to when you decrease the temperature, and it is greater than 1 for temperatures above the ice point. So, it increases, and the way I have plotted, if you are not very careful, you will think it is almost like a straight line, but there is some slight nonlinearity. So, the idea is to see how to characterize this nonlinearity, how to use the platinum resistance thermometer for measurement of temperature. This is what is going to be the discussion from now onwards. The construction details of an RTD are shown in a schematic way in this particular case. We usually take it in the form of an element, resistance element, wound over some kind of a mica or some material like that, and the platinum element is connected to the outside, because we need to take the leads out of that to make the measurement of resistance. And in this case, I have shown a 3-wire arrangement. That means that there are 2 terminals coming from this point, there is 1 and 2, and there is a 3 one. Sometimes we also have a 4 terminal or 4-wire RTD, in which case there will be one more wire coming out from this side, and I will explain later why we have the 3 lead arrangement and the 4 lead arrangement that will become clear when we talk more about the method of measurement of the resistance itself. So, the important requirement is the resistance thermometer should be, the resistance element must be allowed to freely expand, and it should not be confined, and therefore, it should not experience any stresses during the operation of the element, and therefore, it is allowed to freely expand along this direction. It is loosely put inside a sheath material, which is a protective sheath. It may be of either metal or an alloy, and inside that you have a ceramic border, which is going to loosely filled between the element and the sheath, and the platinum element is itself protected from the outside by the sheath itself, and the either the 3 leads or the 4 leads are taken out as shown here. This is only a schematic. The entire dimension of this RTD construction, this may be only a few centimeters in length and maybe a few millimeters in diameter. Here I have shown in a very enlarged view just to make the things clear, and also I have shown very few turns here. Actually, there will be a large number of turns to achieve a 100 ohm resistance at 0 degrees Celsius for a PT 100. So, let us look at the way we are going to characterize the PRT. So, we use some terms which are useful in describing the platinum resistance thermometer. One of them is the alpha value, or it is also called the temperature coefficient of resistance. So, it is defined by the following relation: R of the platinum element at 100 degrees at the ice point, at the steam point, minus R at the ice point divided by, this is actually 100 is nothing but 100 minus 0. I am not showing it as 100 minus 0, just 100. It is nothing but the temperature of the ice steam point minus the ice point temperature divided by R naught. R naught is the resistance at 0 degrees Celsius. So, this alpha is an important characteristic of platinum resistance thermometer. The internationally, the purity of the platinum element is specified, and the alpha value which should characterize that is also specified by giving a value equal to alpha equal to 0.00385 for standard platinum resistance element. This is very important, and I have indicated R naught and R 100 are the resistance values at 0 and 100 degrees Celsius at the ice point and the steam point. If one were to actually use a platinum resistance thermometer, one would like to find out whether it is according to this alpha value is correct or not by actually measuring the R 100 and R 0 and then calculating the alpha value in the laboratory and finding out whether it is agreeing with this within reasonable limits. In fact, the manufacturer will do that and give you a guarantee that it is according to this particular value. So, you can take it if it is a reputed manufacturer. And what I will do is now is to slightly digress, and if you go back to the response relative resistance of temperature, if you look at this curve, it is almost a straight line, but really not. There is slight non-linearity. So, what we would like to do is to see how to take care of this non-linearity. Okay? And this aspect I will cover on the board. I will give a little discussion on that, and I will indicate how we are going to take into account this non-linearity by looking at what is called the calendar equation. I will derive this equation in a very simple fashion. I will indicate the steps. This is the name of the person. Calendar was a scientist who worked with platinum resistance thermometers in the early days of its development, and essentially the calendar equation is basically based on his recommendations and understanding of what was going on. So, I said that the resistance of the thermometer, I will say RT, is the resistance of the platinum resistance thermometer at any temperature T, can be written as R naught into 1 plus A times T plus a small nonlinear term, I will say it is equal to B T square, where B is very small compared to A. This is because slight nonlinearity. And in fact, for the internationally accepted value for A and B are given here. The value of A is 3.90802 into 10 to the power of minus 3, and B value is minus 5.802 into 10 to the power of minus 7. And obviously, B is very small compared to A, because you can see this is 10 to the power of minus 3, this is minus 10 to the power of minus 7, there is a big difference. So, you will appreciate now that when we use the resistance thermometer over a wide range of temperatures, the nonlinearity is going to become important, okay, because B is going to multiply by the square of the temperature, and the square of the temperature, if it is 100, for example, it becomes 10 to the power 4. If it is more than 100, it becomes even greater than that, and therefore, I am multiplying this actually by a factor of 10 to the power 4. You see that it is going to become more or less as big as this term. Okay. So, at high temperatures, when you are using the PRT over an extended range of temperatures to be measured, it is necessary to take into account the nonlinearity. But how are we going to take the nonlinearity into account? That is what we are going to look at now. What we will do is we will define what is called a platinum resistance thermometer scale, platinum resistance temperature, which we call as T subscript PT. Okay. This I will define as a linear scale. This is actually a linear scale, it does not take into account the nonlinearity. So, I will define it simply as RT minus R0 divided by R100 minus R0 multiplied by 100. This is assuming a constant alpha. You remember the alpha, how it was defined. I am using that definition to write the temperature as T subscript PT. Now, let us look at the nonlinear case. So, if I write RT minus R naught divided by R100 minus R naught, RT we know that it is equal to R naught into 1 plus AT plus PT squared. This T is not the platinum resistance temperature, it is the actual temperature I am talking about here. So, when I say TPT, this is the platinum resistance temperature, T is the actual temperature, this is actual, this is the temperature according to the linear scale, this is the linear scale, minus R naught divided by R100. In fact, I can do the following. I can write the R100 as R naught into 1 plus 100 T plus 10 to the power of 4 T square minus R naught. Okay. And this can be further written as, this R naught will cancel with this R naught, and similarly this will cancel with this. This becomes R naught into T, I can take it outside, into A plus BT divided by 100 I can take outside, into T plus 100. I think I left out something here. A plus 10 to the power of 4 B so I take 100 outside, this becomes A plus 100 B. Okay, RT minus R naught divided by R100 minus R naught is equal to R naught will also cancel. T into A plus Bt divided by 100 into A plus 100 B. So, why did I write like this? Because I would like to find out, actually I want to find out T, and what I have written on the left hand side, if you go back to the previous you can see that Tpt is nothing but Rt minus R naught divided by R100 minus R naught into 100, and what I can do now is to substitute that here for the left hand side. Rt minus R naught divided by R100 minus R naught into 100 is Tpt. So, I can write it here as Tpt divided by 100, that is what we are going to do that one. And in fact, what I want to do is to write in the following form. I want to write for T, so T will be this T here, I will cross multiply and so on, this will become RT minus R naught divided by R100 minus R naught multiplied by 100 into A plus 100 B divided by A plus Bt. Okay. This factor, first factor is actually Tpt, this is your Tpt. So, the T is equal to Tpt multiplied by some factor which I want to find out what is that factor in terms of the characteristics of the platinum resistance thermometer, that is means in terms of A and B. So, I can rewrite that as Tpt, that is the first factor, and multiplied by, if I go back and do a little manipulation, you have A plus 100 B divided by A plus Bt. So, I will add plus Bt to the numerator and also subtract minus Bt from the numerator, and so that I can write it in a slightly different form. So, this becomes A plus Bt plus 100 B minus Bt divided by A plus Bt, and this becomes, this gives you 1 plus B into 100 minus T divided by A plus Bt. So, I can say this is Tpt plus Tpt multiplied by 100 minus T divided by A plus Bt. This will be your correction, because the left hand side is nothing but the temperature. And of course, you see, if you look at the second term, you will see that it contains, let me write it back, it contains the temperature again, there is a temperature again. So, what we will do is, we will assume that this temperature can be approximated by the platinum resistance thermometer scale, which is indicated by Tpt, number 1, and number 2, this is A plus Bt, we will assume that in the denominator this term is not as important as this term, therefore, we will neglect this term Bt in the denominator. Okay. If you do that, you will get a very simple expression for the resistance non-linearity. So, we can write it as Tpt plus Tpt multiplied by the value of B by A, if you remember, is minus 5.802 in 10 to the power of minus 7 divided by 3.90802 in 10 to the power of minus 3. This gives you a value of 1.485 into 10 to the power of 4 minus 4. I will write it as 100 squared. And why do I do that? Let me go back to the previous one. You see that if I remove A outside, if I take this A outside and this becomes B by A here and A will come out, this B by A is what I get here, and this B by A is going to be this number for the resistance thermometer, 1.485 divided by 100 squared. This I am going to write as delta. The symbol given for that 1.485 is delta. Therefore, delta divided by 100 squared is B by A. And if I now go back to that expression and write the correction will become simply delta by 100. You can verify that T by 100 minus 1, and I am going to approximate it by Tpt by 100 minus 1. So, this factor delta by 100 multiplied by Tpt multiplied by Tpt by 100 minus 1 is called the C, the calendar correction. And we will notice immediately that when the temperature is 0, this is multiplied by Tpt, temperature is 0, this will become 0, correction is 0 at temperature equal to 0. Again, if temperature equal to 100, you see that 100 divided by 100 minus 1, this becomes 0. Therefore, the correction is 0 at the T equal to 0, T equal to 100, C equal to 0. Actually, what I have done is to make a plot of this, the so called calendar correction. You see that the calendar correction is 0 at the ice point at T equal to 0. It is 0 here, it is also 0 at 100 degrees. That means that these 2 points T equal to 0 and T is equal to 100 degrees, both the resistance thermometer, the platinum resistance scale and the actual temperature coincide, and for all other temperatures there is a correction, and the correction is somewhat small between 0 and 100, the maximum being about minus 0.4 or something like that. And as you go to higher and higher temperatures, I have shown up to about 250 here, the temperature correction could be as big as 6 degrees. What is the advantage of this method of calculation? So, what I will be doing is, I will be calculating Tpt using the linear relationship and then calculate the corresponding value of the correction using the linear temperature which has been calculated and putting into the equation for C, and then I will be able to calculate the temperature without much difficulty. So, the actual temperature is estimated by using the correction based on the linear platinum resistance thermometer scale. That is the advantage of the calendar equation. So, the calendar equation is very useful because without much of a arithmetic or algebraic effort, I will be able to calculate the actual temperature from the linear Tpt scale. Let us look at the details of how we are going to make the measurement of the resistance. This is the important thing which we have to discuss, because we have the temperature detector and it is going to be changing, resistance is going to change with the temperature at which it is going to be, to which it is going to be exposed, and I am indicating the RTD here in this circuit. The RTD is in the one arm of the bridge, and there are two resistances in one of the arms, and the other arm I have got a resistance here which can be varied, and the RTD. There are two ways of doing it. I will just indicate what we are going to do. I have shown here a 3 lead RTD. That means there are 3 leads, one lead here, lead number 2, lead number 3. What is the advantage of using a 3 lead or 3 leads for the correct connection? This point is connected to the battery, and this opposite corner is connected to the battery, and therefore, there are 2 arms of the bridge, one arm consisting of this resistance and the RTD plus this lead wire, and the other arm consists of this resistance, this variable resistance, and the lead wire. Therefore, the lead wire is now going to be on both the arms, and therefore, the lead wire is going to compensate for each other. These 2 and 3, they have certain resistance of their own, and these resistances are going to be in the 2 arms of the bridge, and therefore, they are going to cancel out. And the lead number 1 is going to help us in connecting it to the external world, external battery, which is shown here. So, the 2 and 3 are referred to as the compensating leads, because they are going to be in the 2 sides, 2 arms of the bridge for the measurement. So, if I vary the resistance here, so that there is a balance, because the RTD resistance has changed, the change in the resistance indicated by this one is going to be, if I, for example, I choose these 2 resistance equal in magnitude, these 2 are equal in magnitude at some particular point, let us say 0 degree Celsius. That means, when RTD is at 0 degrees, if I choose such that these 2 are equal, then I will have to choose this equal to 100. If PRT, if the RTD is a PRT 100, PT 100, I am going to have 100 ohms here, for example. Okay. Now, when the temperature changes, this resistance increases, I have to increase this resistance, so that the balance is restored, because if the resistance changes, this resistance arm, this arm, the ratio will be different from this arm, and to compensate for that, I have to change this by an amount equal to the change in the resistance RTD, and therefore, I have to restore the balance, and I can measure the resistance and immediately calculate the TPT by using the linear relationship, and use the correction by calendar to calculate the other one. The second arrangement, which is even better than the first arrangement, is where we have a 4-wire arrangement for lead wire compensation, and there are 4 lead wires I have shown here, 1, 2, 3 and 4. These are the compensating leads, 4 leads are there, RTD is connected, the rest of the connections are the same, the battery and the variable resistance which is in this arm, the 2 other resistances and so on are exactly the same. Now, let me explain briefly the reason for 4 leads, and let us discuss it on the board. I am going to take a look at the arrangement. So, in the first case, this is RB, let me just call that as RA and RB, and the milliammeter is here to indicate the balance. I am just drawing a simple sketch corresponding to what we had. This is the resistance which is going to be varied, RS we will call it, and here we have the RTD with the 4 lead wires, this is the PRT. Let me indicate them like this. Okay. So, I am going to connect this to this here, we will label them as 1, 2, 3 and 4, this I am going to connect here, this is connected to 4 and this is connected to 2, 3 is floating, not connected in the first case, and this is connected to the battery. and this corner is also connected to the battery as we have seen earlier. This goes to the battery, I have already indicated earlier, this corner and this to the battery. So, let us assume that the resistance of the lead wires R1, R2, R3 and R4. So, let us call this as RT, the resistance of the temperature detector, and this will be, we will call it as RS1, the resistance of the, in the first case. Now, I have obtained the balance by adjusting RS suitably. Therefore, you see that if RB and RA are constant, so we know that RT, that is this RT plus R4, this resistance divided by RS1 plus R2. Okay. So, I have taken this resistance, the ratio of these two must be the same as RA by RB. RA by RB equal to this resistance divided by this resistance. Okay. We will call this as equation number 1. If we choose RA equal to RB, if, which can always be done, I will have RT plus R4 is equal to RS1 plus R2, or RT is equal to RS1 plus R2 minus R4. We can call this equation number 2. Now, let us look at the second arrangement, where what I am going to do is, I will have the same, these two resistance no change, and here I am going to change the terminals, this is RT, I will allow the R1 to float, I am going to connect R2 here, and on the other side this will be RS2 in the second arrangement, and this will be connected to R4, and the battery will be connected through R3. This is battery, this is also battery. So, what I have done is I have simply changed 2 and 4, and the connections now R3, which was floating in the first case, is going to be used for the connection to the battery, and by an arrangement similar, the argument similar to what we did in the previous case, we can see that RT in this case is RS2 plus R4 minus R2. So, if you go back to the previous one, R2 minus R4 plus RS1 equal to RT. So, the second case is equation 3. So, if I take the sum of these two, 2RT equal to RS1 plus RS2, these two R4 minus R2 here and R2 minus R4 there going to cancel, and therefore, RT equal to RS1 plus RS2 divided by 2. That means that the lead wire resistance are compensated or cancelled out. So, that means that the resistance of the lead wires are going to be compensated out. We will continue in the next lecture.